Thank you.
Good afternoon or good morning. I would like also to thank you very much for this invitation. I'm very happy to participate at this open event and with such interesting presentations. So I am Olga Mavrouli from the University of West Attica in Athens in Greece. And the topic of my research is landslide risk and mostly quantification of the landslide risk. Previously, I worked at the Technical University of Catalonia in Barcelona and at the University of Twente at the ITC on this topic. So today I will present a part of it. I'm mainly focusing my work on rockfalls. And today I will present a methodology in order to assess the structural performance of masonry walls, which are impacted by rock boulders. So I will start with a very short introduction, just to mention that as it might be well known, the application of the rockfall quantitative risk assessment, the QRA, requires an input for the vulnerability of the building. So for the quantitative risk assessment, we use expressions like this one here, where the risk expressed in quantitative terms, for example, of average annual loss in euro per year, is the sum for all the expected rockfall magnitude sizes and all the expected rockfall kinetic energies of the frequency of a block of a given magnitude multiplied by the probability of reach of this block at a building with a given size and energy multiplied by the vulnerability of the building. We can see different states of damage at different buildings, which also depend on the magnitude and the kinetic energy of the rock and the cost. So in order to quantify the vulnerability, it is required to know whether a block will break the building shell, the exterior walls, and in that case, the extension of the breach. And this depends on the strength of the walls and the rock block size and the impact energy. So although in the literature, there is some significant and very sophisticated work on the damage of structural protection measures, as for example, galleries and nets, the background for the quantitative assessment of the damage for buildings due to rockfalls is poor. And there is a need for quantitative assessment tools for the vulnerability, for the expected damage in that case. And today I will present the work that has been based on what is described in detail in these two presentations, one in the journal Geosciences and the other one at the journal Landslides here. You have both of them here. So the objectives of the work that I will present here are summarized in this slide. The problem is that we have some empirical data worldwide. However, these hardly cover a full range of structural and rock block properties. And in most cases, they don't even provide information about that, about the structural type and the size, the velocity of the rock block. On the other hand, using computational methods, we can have very sophisticated models that take all these properties into consideration. However, these are difficult to be applied at larger scale and time consuming, as well as they required a high level of knowledge in order to apply them, and a lot of parameters, of course. So we wanted to investigate the use of soft computing techniques such as artificial neural networks, ANN, and whether they can provide an alternative for the simulation of this kind of highly nonlinear phenomenon. The objectives were three. First, to develop a big analytical database. So our database has been developed numerically for the training of deep neural networks that calculate the damage of a wall when impacted by rock blocks in terms of the damage index. And that quantitative damage index is equal to the damaged wall area divided to the total by the total wall area. Then, to propose an optimum artificial neural network model for the damage index estimation. And finally, to derive a closed form, an analytical equation that can be directly incorporated into the risk assessment equation that I showed before. So the first step, the first objective, was the development and the application of a methodology for the calculation of the damage index of a wall impacted by a rock block. And the first step consists on the development of a numerical model to calculate the transmitted impact force from the block to the wall. From the block, which is shown here, to the wall. To this end, we use the particle finite element method developed by Oñate and al. At the CIMNE in Barcelona, coupled with a contact domain method, also developed by Carbonet and et al., also at the CIMNE Research Center. And we calculate when the block impacts the wall, the envelope of the maximum contact forces between the two in the direction of the movement, and we extract those maximum contact forces. Three main assumptions that we make for the simplification of the model is that first, masonry and rock are considered homogeneous, elastic, and deformable bodies. Then that the contact between the wall and the block is elastic. This is a slightly more conservative scenario because it assumes that during the contact, the energy is not damped. And we also assumed in this case a cubic block shape for the rock. Another issue that we had to overcome for this model is that during the first contact, the wall would flexure. So that would lead to a concentration of forces on the two corners of the cube and to unrealistic results and instabilities of the code. So in order to overcome this issue, we calculated an equivalent contact force applied tension, which leads to the calculation of the tension, which is applied to the whole edge of the interface between the cube and the wall, assuming equivalence of the impulses between the contact force on the two edges and the equivalent contact force. So the integration of the area under this plot of contact force with time is equal for the contact force and the equivalent contact force. And in that way, we can extract the value of the equivalent contact force and to apply it to the model. The next step was to calculate the damage, and for this we used the finite element analysis software to calculate the stresses on the wall. We used the SAP 2000 combined with the failure software. This is a software that was developed at the National Technical University of Athens, and it incorporates modified von Mises failure criteria for masonries. We have validated this methodology for rocks as well by back analysis of real events. As for example, here we can see the damage with red color due to biaxial tension and with green color due to tension compression in the case of this event here. And after different parametric analysis, we were able to develop a database of 672 datasets, considering the range for 4 different input parameters: the volume of the rock, ranging from 1 to 20 cubic meters, the rock velocity, varying from 1 to 30 meters per second, the thickness of the masonry wall, varying from 40 to 100 centimeters, and the masonry tensile strength, varying from 0.10 to 0.60 megapascal. For the calculation of the masonry tensile strength, we took into consideration the equations, the recommendations provided by Eurocode 6 for masonries that provides an equation for the calculation of the masonry tensile strength given block type and different mortar qualities. So for each one of those combinations of these parameters, 672 combinations, we got a damage index covering a full range from 0 to almost 100%. And we analyzed some statistical correlation analysis we did, and we got the maximum correlation coefficient R, the Pearson correlation coefficient, to be 0.53 and the minimum 0.15. In that case for the rock velocity, and in the case of the minimum correlation for the masonry tensile strength, as we can see here. This leads us to understand that there is a non-linearity of the phenomenon that can be captured with the ANN model. So in order to identify the optimal ANN model, we ran more than 3 million different models. First, we split our data sets into training, validating, and testing data sets. We have a very good size of sample. We tried 6 different optimization algorithms. So we tried data normalization using 4 different techniques, including minimum, maximum, and Z-score. And for each neural network architecture, we used 12 different transfer functions. And after all these different analyses, we came up with the best model characteristics that consists of 24 neurons. It has been optimized by the Levenberg-Marquardt algorithm. The data normalization technique was the min-max, and the normal radial basis and the hyperbolic tangent sigmoid transfer function were used for the input layer and the output layer, respectively. What I would like to show here is the goodness of the fitting. Here we have the analytical damage index values from 0 to 100% and the predicted damage index values, and we can see a very good correlation with a Pearson coefficient 0.9975 and an additional A10 index, which represents the percentage of data sets for which the deviation between true and predicted value is less than 10%, equal to 99.11%. And then we derived an analytical, a closed form equation in function of the input variables. And what's good about this equation is that it can be directly incorporated into the quantitative risk assessment equation, which consists from the damage index normalized. That's a function depending on the 4 input parameters and the 2 transfer functions, the minimum damage index 0, the maximum 100%, and 2 further constants, limits of the minimum maximum normalization technique. And using this equation here, we also developed some plots. We did some mapping. So for different rock volumes, wall tensile, as for example 5 cubic meters, or wall tensile strength 0.20, 0.40, 0.60, and ranges of rock velocity, we get with different values the expected damage index. If we don't want to apply this equation, we can get it directly from the plots here. Just to some final remarks to end this presentation. Using the proposed artificial neural network, the fitted curves were observed to be smooth, which indicates that there is no overfitting. The model works well. What's most important about these results is that this analytical equation can be used for direct integration into the quantitative risk equation. However, it's very important to also mention some limitations. So the first one is that this damage index is a simplified damage index, which refers to the initial impact on the exterior walls, and it does not consider neither the propagation of the rock into the building, nor potential collapse of the building, nor structural damage. So further work should be done in order to incorporate into our methodology these aspects. And of course, this model can be applied only for the range of the parameters that I have shown. So extrapolation in this case is not permitted. I will close my presentation here. I would like to thank you again, Roberto Marin, for his invitation, and of course, all of the co-authors of these two papers, which are also more knowledgeable than me on the topic of machine learning methods. Thank you very much, and if there are any questions, I would be glad to answer them. Thank you very much.